So this is a biased PN junction. You can observe here, this is the p-type semiconductor and n-type semiconductor, where these are called acceptor ions and holes. These are called donor ions and electrons. If I apply positive terminal to p-type and negative terminal to n-type, likewise you can observe here, this is p-type and n-type. P-type and n-type. If I apply positive terminal to p-type and negative terminal to n-type, then it is said to be in forward bias. This is called forward bias first. So in forward bias, what happens is the charge carriers slowly moves from one side to another side. So if you observe here, as we might have already studied here, if I apply forward bias voltage is equal to 0, then there is no current flowing from p side to n side. No current is flowing means no charge carriers are crossing the junction from p type to n type. See the structure here also. So as if it is this, if this one is made up of germanium, if it is made up of germanium, then what happens is slowly its cut-in potential is 0.2. That means below this 0.2, the current is equal to 0. So the meaning of this one is below 0.2, below 0.2 it is a cut-in potential. I can note this one as V gamma as a cut-in potential. V gamma is equal to 0.2, current IF is equal to 0. And this is the point V gamma, which is called cut-in potential, where current gradually increases like this. This is a graph for germanium. Similarly, if the material is made up of this one silicon, then the cut-in potential is 0.6. It starts and gradually increases like this. This is for silicon. And if it is for gallium arsenide, the cut-in potential is 1.2. Therefore, it goes like this. It increases like this. This is for gallium arsenide. So now here, these 0.2, 0.6 and 1.2 are called cut-in potentials. V gamma, they are called cut-in potentials. Cut-in potentials in the sense from that point current starts to flow in the device. It is also called cut-in potential, or it is also called threshold voltage, or threshold voltage. It is also called threshold voltage, or it is also called break point. Break point. So you can call this one with different names: cut-in potential, threshold voltage, break point, or offset voltage. It is also called offset voltage. So it can be called by different names, cut-in potentials. Right? This is in a forward bias, what I'm telling. Now you can see this figure, forward bias, the depletion region decreases actually. Here in forward bias, the charge carriers moves from this point to this point, and from this point to this point. So therefore depletion region decreases, and at a point depletion region is becoming 0. What is that point? Means cut-in potential point. That is V gamma. So depletion region narrows here in forward bias. In forward bias, depletion region narrows. Depletion region narrows. Depletion region narrows. That means decreases. Decreases. Right? This is about forward bias. Come to reverse bias actually. In reverse bias, what happens? In reverse bias, as you might have already studied in regular classes, in reverse bias, I am applying reverse bias potential. What is reverse bias actually? If I apply for p-type, minus and plus for n-type, minus plus, this is called reverse bias. So what happens is all majority charge carriers moves away from the junction. This is a junction. All majority charge carriers moves away from the junction, means they will go like this. They will go like this. And what happens is the depletion region widens. Depletion region widens. So the first and foremost point in reverse bias is depletion region widens. Depletion region widens means increases. And how do this current flow happens? Means it is happened due to minority charge carriers. It is happened due to minority charge carriers. It is happened due to minority charge carriers. Whereas in forward bias, current is happened due to majority charge carriers. Majority charge carriers. So what are these minority charge carriers? Here in p-type electrons and n-type holes are minority charge carriers. So what happens is, as I increase reverse bias potential here, this is reverse bias potential. As I increase reverse bias potential gradually, what happens is, slowly the current is increasing. It reaches a point which is called VBR, which is called breakdown voltage. It reaches a point called breakdown voltage. From that point, the current gradually increases, and this is said to be in breakdown region. This is said to be in breakdown region, and this reverse bias current, it is in microamperes for germanium, and it is in nanoamperes for silicon, and it is in picoamperes for gallium arsenide. Please do remember, micro means 10 power minus 6, nano means 10 power minus 9, and pico means 10 power minus 12. 10 power minus 12. So in this breakdown region, diode may break because we are applying a potentials greater than 25 volts. If I apply greater than 25 volts, in order to make sure that current has to be happened in due to minority charge carriers in reverse bias. So therefore, temperature is increased. As temperature increases, heat increases. So therefore, bombardment of charge carriers increases. And this process, actually it is called as avalanche multiplication. Actually, more number of charge carriers are created in reverse bias, because one minority charge carrier collides with another atom of minority charge carriers which are present at outermost orbit. It will collide. Suppose if it collides, then it will be released into the space one electron, and this first electron comes over here. Again, these two electrons goes and collide with another atom, and therefore releasing how many electrons? 4 electrons. 1 2 3 4. Likewise, 4 electrons will be colliding with another 4, then it will be 8, 16, 32, 64. Likewise, the count goes 128, 256, 512. So 512 charge carriers have been created in reverse bias. That too, these are minority charge carriers that are created. So in turn, creating a large amount of current flow. So this current cannot be withstood by the device, and the device is said to be in breakdown condition. So this process is called avalanche multiplication. This process is called avalanche multiplication. This process is called avalanche multiplication or carrier multiplication or avalanche breakdown. Avalanche breakdown. So suddenly current is rising, and therefore see here, see the curve, suddenly current rises and therefore device may break. Right, but here in depletion region widens here, right? Depletion region widens here. This is a point you need to remember here. Depletion region widens. And these are about characteristics in forward bias and also in reverse bias. And do remember here, germanium it is in microamperes, silicon it is in nanoamperes, gallium arsenide it is in picoamperes. Right, now let us see here some important topics you need to learn regarding gate here. Suppose this is a depletion region here, what we have observed here. Here in this depletion region, there presents a immobile charge. What is that immobile charge? Suppose, for example, here this complete thing is a donor ion. This is a donor ion which is having a hole. Donor ion which is having a hole. Donor ion having a hole. So likewise here, wherever you see donor ion and a hole will be present here. As we have explained in the last class as donor ion and a hole, donor ion and a hole, donor ion and a hole. But what is present here in depletion region? Only ions. That too, what is this ion called? Immobile ion. Immobile ion. Because the holes and electrons have been recombined here. What is present here? What is present here means donor ion. These are called acceptor ions. No, these are called acceptor ions. These are called acceptors ions, and this is called as a hole. What is this one called? It's a donor ion. It is called as donor ion, and this is called as an electron. So likewise, complete structure of n-type semiconductor, it is contained by donor ions and electrons. Donor ions and electrons. Donor ions and electrons. Donor ions and electrons. But what is present here near the junction? It is just an immobile charge, which is a positive immobile charge. Plus, because the electron is getting recombined with the hole nearby it near the junction. So therefore, only positive charge is present here, as you might have studied already in last class. So this is called depletion region, right? Now here what I am doing is I am taking the width of this depletion region as the width of this depletion region from this point to this point as this width is in p-type, so therefore I can write this one as WP. So this width I am taking W is a width of depletion region, and this width I am taking as WN. WN. What is the total width of depletion region? I can take this one as total width of depletion region as W. W. So what is W is equal to ma? What is W is equal to? Total width of depletion W is equal to WP plus WN. This is actually total width of depletion region. W is equal to WP plus WN. Now I can consider here this total concentration as acceptor concentration as Na, and this total concentration as a donor concentration Nd. Donor concentration Nd. Now there is a relation between Na, WP, Nd, Wn and W, right? So what is that? See, let us see here. The relation is like this. The relation is like this. Charge on, always do remember that charge on P side is equal to charge on N side. I can write this one as charge on P side is equal to charge on N side. I will go with another slide here. Very important derivation here. Charge on P side is equal to charge on N side. Say I am drawing again here. This is P type. This is called depletion region. This is P type and this is N type. This is the depletion region. What is the width of this one? Width of this one is WP. Width of this depletion region is WN. And here acceptor concentration will be present. Here donor concentration will be present. Right. Total width of depletion region from this point to this point is W. So what is W is equal to WP plus WN. See, most of the questions are asked in the gate in this format only. See. Now here charge on P side. Charge on P side is equal to charge on N side. So always semiconductor is a neutral one. So therefore we can write this one as charge on P side is equal to charge on N side. What is charge on P side? I can write charge on P side as charge density into volume on P side. Very important, volume on P side. Charge density into volume on P side. Here also charge density in N side, charge density into volume on N side. What is charge density? It is given by rho P. I already told you rho P. And what is volume on P side? Volume is equal to area into width. So what is area? Area I can write as area into width. What is width on P side? WP. That is equal to what is charge density on N side? Rho N into what is volume? Area into WN. What is charge density? Rho P. How do you write rho P? Rho P can be written as it is equal to PE for P-type semiconductor. PE for p-type semiconductor, and rho n is equal to, that is equal to Ne for n-type semiconductor. This one we are already studied, right? And PE is also written as what? P can be written as what? Acceptor concentration, Na into E. And here what is N can be written as donor concentration, Nd into E. So right here, what is rho P? Rho P is equal to Na into E into area into Wp. That is equal to rho N. Rho N is Nd into E into area into Wn. So area cancels, E cancels. So what is the equation? Na into Wp, that is equal to Nd into Wn, or this is the equation, or this equation can be written as like this: Wp divided by Wn, width on p side is equal to depletion region width on n side divided by Wn is equal to how much? Nd divided by donor concentration divided by Na. This is a very important equation. Very important equation. Now the gate questions comes here like this. In p side, if in p side what happens? In p side, if the semiconductor is a p-type semiconductor, what happens? Case 1. If the semiconductor is a p-type semiconductor, what happens? Acceptor concentration is greater than donor concentration. Then the question will be asked like this: in p-type, if the semiconductor is a p-type semiconductor, then what about their depletion region width? What about their depletion region widths? Here Wp is called depletion region width towards p side. Depletion region in p side. Wp is called depletion region in p side. Got it, Amma? Depletion region in p side. What is Wn? Wn is called depletion region in n side. Now tell me, the question is, even p-type, if the semiconductor is p-type semiconductor, then acceptor concentration is greater than donor concentration. So what about the depletion regions? What about the depletion regions? Na is greater than Nd. So what about depletion regions? Depletion region, if Na is greater than Nd, Na is greater than Nd, what happens? Wn, what about, see, if Na is greater than Nd, there is a more possibility that all these charge carriers present in p-type diffuse more into Nd. So therefore, what will increase here? Width of depletion region in n-type increases. So Wn is greater than Wp. Wn is greater than Wp. So always do remember, if doping concentration in one side increases, then the other side depletion region increases. Case 2, in N, if the semiconductor is n-type semiconductor, then what happens, Amma? Nd is greater than Na. If Nd is greater than Na, what happens to depletion region? Depletion region is Wp is greater than Wnc. There is a possibility that more electrons here, if it is heavily doped, Nd greater than Na means donor concentration is more compared to acceptor concentration. So donor concentration is present in n-type semiconductor. So therefore, more charge carriers here. What happens? There is a possibility that they will diffuse more into p-type. Diffuse more into p-type means they will recombine here with the holes present in p-type. So therefore, depletion region increases. So what is depletion region? Actually, the recombination elements which are, it's nothing but an area where recombination elements are present. So therefore, here more recombination, so therefore depletion region increases in p-type. So that's what Wp increases here. So here this is the relation: depletion region Wp is greater than Wm. Wp is greater than Wn. So this is the most important point you need to remember here, right? And the another point you need to remember here is that junction capacitances. Junction capacitances. The junction capacitance. Near the junction, what are the capacitances that are found here? See, junction capacitance. What is that junction capacitance? Junction capacitance, it is being divided into two types. Junction capacitance. One is diffusion capacitance, which is observed in forward bias. See, it is observed in forward bias. It is observed in forward bias, and this is observed in reverse bias. This is observed in reverse bias. What is observed in forward bias means the capacitance. See, you can observe here. So this is a structure, P type and N type. This is P type and this is N type. A small depletion region will be there here in forward bias before current flow exists. So this depletion region is called as diffusion. See, this is a capacitance color. See, you can observe here what charge is present here. This is minus, minus, minus. What charge is present? Plus, 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 plus. So minus, plus, minus, plus means it's a meaning of a capacitance. A capacitance like this. This is a minus and this is a plus. This is a shape of a capacitance. This is a shape of a capacitance. So this capacitance is called diffusion capacitance. So please, very important point in for competitive exams, capacitance observed in forward bias is called diffusion capacitance. Capacitance observed in forward bias is called diffusion capacitance, or it is also called storage capacitance, or it is also called storage capacitance. Storage capacitance. Now, what current exists in this in forward bias? Actually, forward current exists. Right. Forward current exists means it is due to majority and minority carriers. Majority charge carriers. It is due to majority charge carriers. It is due to majority charge carriers. It is due to majority charge carriers. And here I am directly writing a formula which is existing for diffusion capacitance, because this diffusion capacitance is given by CD, C suffix D, and this C suffix D can be written as CD is equal to tau I divided by neta Vt. Tau I divided by neta Vt, where tau is called time period, I is called forward current, neta is constant, 1 for germanium, 2 for silicon, Vt is called volt equivalent temperature. So CD is equal to tau I divided by neta Vt. Now here the important equation is diffusion capacitance is directly proportional to I. That is, if forward current is increasing, what happens to diffusion capacitance? It also increases. Right, that is one point. The next point, next case is, what about as temperature increases? As temperature increases, what happens to CD, diffusion capacitance? As temperature increases, because Vt is equal to Kt by Q. So CD is inversely proportional to 1 by T. So as temperature increases, diffusion capacitance decreases. Diffusion capacitance decreases. Right? So, and diffusion capacitance is directly proportional to forward current I. I increases, diffusion capacitance increases. Okay, right. Right, next. Come to reverse bias. This is about forward bias capacitance. Come to reverse bias. Reverse bias, just now we have learned. Reverse bias, if you see the reverse bias, depletion region is widening. In reverse bias, depletion region widens. This is the depletion region in reverse bias. If this is a p-type semiconductor and this is n-type semiconductor, in reverse bias, as we apply reverse bias potential, depletion region widens. So here minus, here immobile charge, negative immobile charge, negative immobile charge, negative immobile charge. Here positive immobile charge, 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 this one. Right? So this is immobile charge, that's what this region is called, depletion region. Right? Now This is a capacitance. Please do understand. I told you just now minus and plus combination. Here also many minus and many plus combinations are there. So this minus and plus combinations is nothing but a capacitance. Minus is written like this and plus is written like this. This is nothing but a capacitance, and this capacitance is called transition capacitance. Capacitance which is observed in reverse bias is called transition capacitance. Capacitance which is observed in a reverse bias is called transition capacitance. Transition capacitance. Or it is also called space charge capacitance. Or it is also called space charge capacitance. Space charge capacitance. Right? And this is occurring especially in reverse bias. Please do remember, this is occurring especially in reverse bias. Again, this space charge capacitance is being divided into two types. Right, linear graded and step graded. Linear graded means equal doping among both sides. Both sides of depletion region, it is equally doped. So it is equally doped. Equally doped. Or what is the other one? Other method is step graded junction. Linear graded and step graded. Step graded means it is non-equally doped. That is, unequal doping is happened here. Unequal doping. Please do remember, these are all very important for competitive exams. Unequal doping is happened in a step graded junction. Equal doping is happened in linear graded junction. Right? So here equal doping means you have a depletion region like this. You have a depletion region like this for negative and like this for positive. Right? And what about this one? Means this is nothing but width of depletion region. I can write this one as minus W by 2 and this is plus W by 2. Width of depletion. If you add it, you will get a complete width of depletion region as W. So this is equally doped. That's what you get, linear graded junction like this. What about step graded junction? It is non-uniformly doped and you have a step graded junction like this. In an N type you have a large depletion width because it is non-uniformly doped, and in P type you have short depletion width, this one. So this is the depletion regions in N type and P type respectively. Right? And therefore here this transition capacitance is given by C suffix T, and this transition capacitance CT can be directly written as like this: epsilon A by W. Epsilon A divided by W. Epsilon A divided by W. Epsilon is a permittivity. A is a area and W is a width of depletion region. W is width of depletion region. Now some points you need to mention here. CT, transition capacitance, is inversely proportional to width of depletion region. So width of depletion region increases, what happens to transition capacitance? Decreases. If width of depletion region decreases, what about transition capacitance? It increases. So these are the important points you need to remember here. This is regarding transition capacitance and diffusion capacitance. Right. Please go through this formulas under this slide. Very important for you. If you have any doubts, please let me know that. This is regarding junction capacitance. That is regarding junction capacitance. Anyhow, at last we will do some problems regarding all this what we are studying regarding PN junction diode. Okay, this is the junction capacitance what we have observed. You can verify it, and the important formulas what I have kept in the box. Na into Wp is equal to Nd into Wn. Wp by Wn is equal to Nd by Na, and Ct is equal to epsilon A by W. Cd is equal to tau I by neta Vt. that is for diffusion capacitance, and transition capacitance is epsilon A by W. And the doping concentrations and width of depletion regions you can write there, and total width of depletion region W is equal to WP plus WN. WP plus WN. So please note all these points. If you have any doubts, please let me know that, because these are very important for you. Right? Completed. Right. Next, we'll go for the same continuation topic. We'll go for derivation for potential energy barrier and width of depletion region. Right. Let us calculate what is the potential energy barrier and depletion region width. Just now I told you. If you see the structure of this one PN junction diode, this is P type and this is N type. Let us derive this potential energy barrier. What is this potential energy barrier? It's a height, man. It's a height. If a charge carrier wants to move from P type to N type or from N type to P type, it has to overcome that barrier, right? So how much potential we need to apply to overcome that barrier? This is nothing but potential energy barrier. This one. Suppose hole, if it wants to move from P type to N type, it has to overcome this potential energy barrier, which is called as plus, which is present here. And if an electron wants to move from N type to P type semiconductor, it has to overcome a minus potential energy barrier here, right? So this is called as a potential energy barrier, and it is given by, or it is also called built-in potential. It is given by VBI, built-in potential VBI, or sometimes it may be also called as or B, capital B, built-in potential or barrier voltage, right? Now here, as we have already studied, here there occurs acceptor concentration, here donor concentration is observed, and here the width of this depletion region towards P side is WP, towards N side is WN, and total width is W, where W is equal to WP plus WN. And in we have derived one formula in last slide, that is equal to NA into WP is equal to ND into WN. ND into WN. Now let us see. In order to calculate this potential energy barrier, then according to Poisson's law, we have an equation called Poisson's law. According to Poisson's law, according to Poisson's equation, we have an equation called d square v by dx square is equal to rho by epsilon, d square v by dx square is equal to rho by epsilon, right? From this equation, let us prove the potential energy barrier. So first integrate this Poisson's equation on both sides. Integrate on both sides. What you get? Integration d square v by dx square, integration d square v by dx square in terms of dx, that is equal to integration rho by epsilon to dx. So what do you get, Amma? This is equal to, you get here dv by dx, because integration d square v by dx square is equal to dv by dx, that is equal to rho by epsilon. Rho by epsilon is constant, so what you get is rho by epsilon, and here we are integrating with respect to with respect to width of depletion region, or you can write this one as x also, x, right? So rho x by epsilon I got. Again integrating on both sides, again if you integrate dv by dx is equal to rho by epsilon integration x dx. So what do you get here? Integration dv by dx is what do you get? V, that is equal to integration dv by dx is v, that is equal to rho by epsilon into x square by 2, rho by epsilon into x square by 2. So now I got this one. This is called as a potential, which is called as a built-in potential. This built-in potential is given by VBI, that is equal to rho by epsilon into x. I can consider x is equal to as the width of depletion region, so therefore I can write as w square divided by 2. So here rho is nothing but what? Rho, I told you already, rho is equal to, it is equal to PE for p-type semiconductor, or it can be written as PE means Na into E, or E is also called Q, and rho is also equal to Ne, that is equal to N means what? Donor concentration, Nd into Q. So therefore here I can write here instead of rho like that, it may be PE or it may be Na. So therefore here, for example, if it is a p-type semiconductor, built-in potential is equal to, I can write like this for p-type semiconductor, E Na or Qna, E into Na, this one, this is also equal to Na into E, this is also equal to Nd into E. So for p-type semiconductor I am writing as E Na into W square divided by 2 into epsilon, 2 into epsilon. So from this what is width of depletion region? W is equal to, it is square root of, it is square root of 2 epsilon VBI whole divided by E into Na, E into Na. This is the width of depletion region, width of depletion region. Or what is the other one? If it is n-type semiconductor, what is the width of depletion region? Or it can also be written as width of depletion region for W is equal to square root of 2 epsilon VBI whole divided by E into Nd, E into Nd. This is for n-type semiconductor, 2 epsilon VBI divided by E into Nd. This is called as built-in potential VBI, right? Built-in potential VBI. Now here see what is dV by dx actually. What is dV by dx? dV by dx is also called as electric field intensity E. So there is another formula which existing here like this. dV by dx can also be written as electric field intensity E. But this electric field intensity E can be written as rho. For example, rho is equal to, I am writing for p-type semiconductor, it's equal to how much? Na into E, or E into Na, E into Na into x. In terms of x, I write here width of depletion region, which is equal to, because it's a p-type, so Wp divided by epsilon. So this is electric field intensity formula, very important. Electric field intensity formula is rho Wp divided by E, or if it is a p-type semiconductor, then you can write it as E Na Wp by epsilon, right? What is the other formula for n-type semiconductor? Electric field intensity E is equal to E into Nd, E into Nd into Wn divided by epsilon, This is another formula for electric field intensity for n-type semiconductor. For n-type semiconductor. See these are all very important expressions that you need to remember. Very important expressions. Please follow carefully. Electric field intensity depends on width of depletion region towards p-type and n-type. Electric field intensity in p-type and n-type, and also built-in potential, which is called VBI. Right? Now see, Let us calculate what is width of depletion region in N type and what is width of depletion region towards P type. This is actually total width what we have studied now, width of depletion region. Now if you want to calculate what is width of depletion region towards P type and N type, now the equation will be followed like this. As we know, actually V is equal to, this is the equation. From this equation, from equation 1, what is V? V is equal to built-in potential VBI, that is equal to rho into W square divided by 2 epsilon. Now rho consider for both P type and N type semiconductors. If you consider rho for both P type and N type semiconductors, what will be the formula? It is equal to E. Previously we have written only for acceptors and acceptor concentration separately and donor concentration separately. Now combine this acceptor and donor concentrations, you get for both the semiconductors E into Na plus Nd and divided by 2 epsilon, and here W square I am writing it as a Wp for P type semiconductor and Wn for N type semiconductor. So I am writing like this, Wp and Wn. So E into Na plus Nd divided by 2 epsilon. Right. Now what happens for N type semiconductor? This is for both the type of semiconductors. Now let us write it for exclusively for N type semiconductor. Exclusively for N type semiconductor, what happens? For N type semiconductor, built-in potential VBI is equal to E into Na plus Nd whole divided by 2 epsilon and if it is N type semiconductor, this Wp should not be there, right? What is Wp in terms of Wn? What is Wp in terms of Wn? That is important. See this equation. What we have actually, Na, what we have actually, Na into Wp is equal to Nd into Wn. Right. Now what we want actually, Wp. So what is Wp is equal to Nd divided by Na into Wn. You substitute this one. You substitute this equation. Here. What you get? Instead of Wp, I am writing as Nd donor concentration divided by Na acceptor concentration into Wn. Already Wn is there, so I am writing Wn here. So what I get here? Now built-in potential VBI is equal to E into Na plus Nd divided by 2 epsilon into Nd by Na into Nd divided by Na into Wn square. So what we want actually, width of depletion region towards N side, Wn. So what is width of depletion region now? Wn is equal to how much? Wn is equal to, you get here, what do you get here? Square root of, what do you get here? Cross multiply it, what do you get? 2 epsilon VBI into Na divided by Nd whole divided by E into Na plus Nd. So this is the expression for width of depletion region towards N side. This is the expression, right? This is width of depletion region towards N side. Width of depletion region in the N side. Similarly, can you tell me what is width of depletion region towards P side? From the same equation. Here I have substituted for WP ND by NA into WN. Right. Now you substitute instead of WN, you substitute here. Instead of WN, what you get? NA divided by ND here. Here, using this equation, WN is equal to NA divided by ND into WP. Then what you get? The same equation. What you get here? WP is equal to square root of 2 epsilon built-in potential VBI into ND divided by NA whole divided by E into NA plus ND. So this is the width of depletion region towards P side. The same equation similarly, just you substitute instead of WN, what you substitute is WN is equal to, if you substitute NA divided by ND into WP. If you substitute here this WN value into this equation, then you get this equation. So 2 epsilon VBI ND by NA into divided by E into NA plus ND, right? So I write this one as second equation and I write this one as third equation. Now this is a width of depletion region in N side and this is width of depletion region towards P side. What is total width, Amma? What is total space charge region width? I can write total space charge region width, depletion region width, W is equal to WP plus WN. Now substitute these 2 and 3 equations into W here and get me the answer. What do you get? W is equal to WP plus WN. So what answer you get? Get me the value. W is equal to, I'm going for a next slide, Amma. If you have any doubts, please let me know that. You can unmute your voice and then tell me. W is equal to WP plus WN. Say I'm going for this one. WP is equal to total width, W is equal to WP plus WN. Substitute here. What do you get? W is equal to, WP is 2 epsilon VBI ND divided by NA whole divided by E into NA plus ND whole power 1 by 2. Square root means I am writing here it's whole power 1 by 2 plus 2 epsilon, what is WN? 2 epsilon VBI into NA divided by ND whole divided by E into NA plus ND whole power 1 by 2. Now if you want to simplify this equation, square on both sides. Squaring on both sides. Let us simplify this equation. Squaring on both sides and get me the expression for W, ma. Squaring on both sides. What do you get, ma? What do you get? W square you get here, and this is A power 1 by 2 plus B power 1 by 2 whole square. A is this one and B is this one. A power 1 by 2 plus B power 1 by 2 whole square. So A plus B whole square. If it is A plus B whole square, then what is the equation, ma? W square is equal to A square. A square means A power 1 by 2 whole square. What do you get? Square 1 by 2 gets cancelled. So you get here 2 epsilon VBI into ND divided by NA whole divided by E into NA plus ND plus B square. B square is 2 epsilon VBI NA divided by ND whole divided by E into NA plus ND plus 2AB. This is equal to a square plus b square plus 2ab. What is 2ab, ma? 2 into square root of 2 epsilon VBI ND divided by NA whole divided by E into NA plus ND whole power 1 by 2 into 2 epsilon VBI to NA by ND whole divided by E into NA plus ND whole power 1 by 2. This is 2ab, a square plus b square plus 2ab. Now that is equal to the same thing you write here, the same thing you write here, plus you simplify this one. What do you simplify? You get what answer you get? This is square root. Square root means what answer you get? Tell me. This I can make it as only single square root, and what answer I get here? 2 multiplied by 2 epsilon VBI to ND by NA into NA divided by ND whole divided by E square into NA plus ND square. So this is whole power 1 by 2. What happens? NA, ND, ND gets cancelled. So what remains, ma? The same thing here. W square is equal to first term is same, second term is same, plus 2 times of what, ma? 2 into 2 times of 2 into what remains here? 2 epsilon VBI divided by square root E square. How much, ma? Square root E square. Here also 2 epsilon VBI square. 2 epsilon VBI square. Square root gets cancelled. Here E square root cancels. E into NA plus ND. E into NA plus ND. 2 epsilon VBI by E into NA plus ND. Right? Now this is the equation. From this equation, W square is equal to what is the first term, mama? Take out common in both first, second and third terms. 2 epsilon VBI divided by E into NA plus ND. So I am taking out 2 epsilon VBI divided by E into NA plus ND. Take out common. So what remains in the first term, mama? What remains in first value? The first value remains ND by NA plus what remains in second term? The second term remains as NA by ND. You can check it. NA by ND plus what is this one? 2 epsilon VBI. What it remains? It remains as 2 because I am taking out common here. Right? Now take out LCM here. This is equal to 2 epsilon VBI divided by E NA plus ND. Take out LCM here. What is LCM here? NA into ND. LCM is NA into ND. So if it is NA into ND, what happens here? You get ND square. What do you get here? NA square you get here plus 2 into NA ND you get. Right, that is equal to 2 epsilon VBI divided by E into NA plus ND into what is this one? ND square plus NA square plus 2 NA ND can be written as NA plus ND whole square. NA plus ND whole square all divided by NA ND whole divided by NA ND. So what happens? This square and this one cancels. What is this one is equal to 2 epsilon VBI into NA plus ND whole divided by E into NA ND, that is equal to W square is equal to split into two parts, 2 epsilon VBI divided by E into, I can write like this, NA divided by NAND plus ND divided by NAND. So nothing changes. Here ND cancels, here NA cancels. What remains now? W square is equal to 2 epsilon VBI divided by E into 1 by ND plus 1 by NA. So this is W square. But what is W? W is equal to square root of 2 epsilon VBI by E into 1 by ND plus 1 by NA. This is the answer for width of depletion region. This is the answer for width of depletion region. Total width of depletion region. Total width of depletion region is equal to 2 epsilon VBI by E into 1 by ND plus 1 by NA. Now here, what is this built-in potential? This built-in potential here, you can assume here, if this is the diode, P-type and N-type semiconductor, this is the depletion region. And what is this depletion region barrier height? It is always given by V0, as I have discussed already in the first class. This is called barrier height for P-type. If a hole wants to cross the junction, then it has to overcome this barrier height V0, right? So this barrier height V0, it depends upon what? It depends upon whether we are applying forward bias or reverse bias. So suppose if you apply forward bias VF, then what is this? This complete thing is called built-in potential or barrier height. It is given by VBI, right? Now here this equation represents for unbiased junction. This equation represents for unbiased junction because we are not applying any forward bias and reverse bias. Suppose if we apply forward bias, what happens to VBI? What happens to VBI? It decreases or increases. Suppose if I apply forward bias here, forward bias is increased. What happens to this width? Decreases. What it is decreasing? V0 decreases because depletion region width decreases. No, so therefore, for biased junction, what happens? For biased junction, VBI is equal to, for biased junction, built-in potential VBI is equal to, it is equal to V0 minus, if it is forward bias, it is equal to V0 minus VF, because V0 is decreasing. No, so this is for forward bias. For biased junction, forward bias. What about reverse bias? Can anyone tell me what about reverse bias? What is built-in potential is equal to? For reverse bias, VBI is equal to V0 minus of minus. Reverse bias means depletion region increases, so barrier height increases. Increases means here minus already is there. Minus of minus is plus VR. VR is reverse bias. This is for reverse bias. Now if you substitute this VBI is equal to V0 minus VF, VBI is equal to V0 plus VR for here, then you will get for both biased junctions. This VBI should be replaced by V0 minus VF for forward bias and V0 plus VR for reverse bias. Then width of depletion region will exist for biased junctions. Width of depletion region is existing for biased